Hello friends, welcome to this lecture. In this lecture we will continue our study of green function, and with the help of green function how to solve the non-homogeneous problem, and we have seen one example in previous lecture. So, in previous lecture we have discussed how to construct green function for homogeneous self-adjoint equations, and also we have seen how to make linear ordinary differential equation to self-adjoint linear differential equation, and how to convert non-homogeneous boundary condition to homogeneous boundary condition. Now let us proceed further and discuss how to use green function method to solve the non-homogeneous linear ordinary differential equation. So here this is the theorem. Consider the following non-homogeneous equation: P naught x y double dash x plus P naught dash x y dash x plus P2 x y x equal to f of x. Please note down here that the coefficient of y dash is P naught dash x. So it is basically a self-adjoint non-homogeneous linear differential equation. So it is Ly equal to f is the equation given here, and the boundary conditions are given as v1y and v2y, where v1y is alpha 1 y a plus beta 1 y dash a equal to 0, and b2y is alpha 2 y a plus beta 2 y dash b equal to 0. So here this is the condition given at the point x equal to a, and this is the condition given at the point b here. So here v1 and v2 are linearly independent. Also let y1 and y2 be two linearly independent solution of Ly equal to 0, such that it satisfies these two boundary conditions respectively. So y1 is a solution which satisfy Ly equal to 0 and satisfy the first condition, boundary condition, and y2 be another solution which satisfy the second boundary condition. And here we say that if gxi is a green function of the homogeneous boundary value problem Ly equal to 0 with the boundary condition vky equal to 0, where k is from 1 to 2, then yx is a solution of boundary value problem 51-52, that is non-homogeneous equation with homogeneous boundary condition if and only if yx is given by a to b gxi f xi d xi, where gxi is given as y1x y2 xi divided by p naught xi w xi, which I denote as g1x xi, and it is given in this domain from x from a to xi, and g2x xi which is given by y1 xi y2x divided by p naught xi w xi, and x is from xi to b. And please note down here that this p naught xi w xi is a constant given at a, and we have already discussed how to get this constant using Lagrange's identity. So it means that if green function is given for this homogeneous boundary value problem with homogeneous boundary condition, then the following formula for y of x will solve the non-homogeneous equation with homogeneous boundary value problem, where gxi is we have already obtained in previous lecture like this. So that theorem we have given in previous lecture, we have just stated but we have not proved. In this lecture we wanted to prove the given theorem here. So let the relation 55 is true. So 55 is true means yx equal to yx is given by a to b gxi f xi d xi, and then we want to show that it is a solution of the non-homogeneous boundary value problem. So we have to show that if yx is given by this, then it satisfies the problem Ly equal to f of x. So for that we have to show that that y satisfies this non-homogeneous equation. So for that let us write down yx equal to a to x gxi f xi d xi plus x to b gxi f xi d xi. So here we have just truncated into two part depending on xi. Xi is less than or equal to x and xi greater than or equal to x. Now in xi less than or equal to x, we have gxi is given by xi less than x. So xi less than x means here. So here we use this value gxi is y1 xi y2 x. divided by a. So, y1 xi y2 x divided by since a is constant we can take it out, d xi plus x to b. Now, here g x xi means xi is greater than or equal to x. Now, look at xi greater than x means xi here xi is greater than x means xi is greater than x means here. So, here we are using y1 x y2 xi divided by a. So, here we are using y1 x y2 xi divided by a, that we have taken out. So, yx is given by this thing. Now, here a is your p naught x w Wronskian of y1 y2 given at point x, and we know that this is constant. So, now yx is given here. Now, differentiate with respect to x. So, when you differentiate with respect to x, what you will get? Let me write it here. So, y dash x is equal to 1 upon a as it is. Now, here if you differentiate with respect to x, please. So, here we can differentiate it like this, that a to x, and inside it is y2 dash x y1 xi f xi d xi plus. Now, since integral involves your x, so here we use Leibniz formula of differentiation under the sign of integration, and you will get this as here you put xi equal to x. So, it is y2 x y1 x f of x and differentiation of x. So, it is this so this is plus, okay, plus when you integrate this, it is what? A to b y2 xi y1 dash x f xi d xi minus, now it is in a lower, so it is minus here y2 x y1 x f of x, that is all. So, if you look at this, will cancel out, right. So, what you will get? Y dash x equal to 1 upon a to x y2 dash x y1 xi f xi d xi plus a to b y2 xi y1 dash xi f xi d xi. Now, when you differentiate it again, what you will get? Y2 y double dash x equal to 1 upon a, here you will get a to x y2 double dash x y1 xi f xi d xi and plus. Now, I will write it here y1 dash x y1 x f of x plus x to b, sorry, this is x to b. So, x to b and y2 xi y2 double dash x f xi d xi, I think it is y1 dash x minus, here we have y1 dash x y2 x f of x. Now, if you look at this quantity, this is basically what? This is y1 dash sorry, it is something, it is y2 dash, it is y1 y2 dash minus y1 dash y2 into f of x, and that we can write it, this is what? Wronskian of y1 y2 into f of x. So, and so if you write it, so it is what? A to x y2 double dash x y1 xi f xi d xi plus x to b y1 double dash x y2 xi d xi into f of x, f of xi d xi here, and if you take it out, the term what will get is f of x, your Wronskian of x here, Wronskian of y1 y2, and we already know that this quantity is what? This quantity is basically and divided by a. So, that you can take it out. Now, a is basically p naught x w x. So, we will if you use the a value of a, that is p naught into w x. So, this will cancel out, we have f of x into p naught x plus this quantity 1 to a to x y2 double dash x y1 xi f xi d xi plus x to b y1 double dash x y2 xi f xi d xi. Now, when you substitute the values of y double dash, y dash and y and calculate this quantity, that p naught y double dash plus p1 y dash plus p2 y, you will see that it is what? It is inside, if you multiply here then we have only f of x plus 1 upon a, and if you look at inside you will get what? Inside L of y2 in integral L of y2 a to x, let me write it here in a separate thing. So here we want to calculate this p naught y double dash plus p1 y dash plus p2 y, and it is f of x divided by p naught into p naught plus 1 upon a, and here let me collect all these things, and it is a to xem, and when you collect you will get L of y2 of x, y1 xi, f of xi d xi plus, and x2 b here, then you will get L of y1 y2 xi, f of xi d xi, and so on. So that is what we will obtain here. Okay, so if you collect the remaining term here. So now we already know that this L of y2 is a y2 is a solution of L of y2 satisfying the boundary condition. That is not required, in fact L of y2 is equal to 0, similarly L of y1 is equal to 0. So using this is simply gone. So what is left is that f of x. So it means that L of y is given as f of x, where y is given as a to b and g xi f of xi d xi. So we have shown that if yx is given by a to b, g xi f xi d xi, where g xi is defined as g1 xi, g2 xi, x less than xi, x greater than xi, then your Ly is equal to f of x. That yx will solve the non-homogeneous boundary value problem. So that is the content, that is one way. Now we want to show that it also satisfy the boundary conditions. So boundary conditions are what? That is vky equal to 0. So here just note down that look at this particular problem. So here if you look at y of a will be what? So if you look at y of a, you will get this a to b, and here you will get what? y1a. So y1a you will get y1a, and this is y2 xi f xi d xi, and similarly your y dash a will be what? Y dash a will be simply a to b, and y1 dash a you can take it out, y1 dash a, y2 xi f of xi d xi. Now ya you can take it, ya you can write it from this this equation, and y1 dash a you can get it from this. Similarly you can get yb and y dash b from these set of equations, and then you can verify, I am leaving it to you, that it also satisfy the boundary condition vk y equal to 0. So I am not doing it because it is going to be a little bit lengthy. So now let us look at the converse part. The converse part means that once we have g xi, then basically it will also satisfy the relation that a to b g xi f xi is basically y of x. So let us start with this part, and you show that this is equal to your y of x. So for that you just calculate this a to b g xi f of x d of x. Now here we already know that f of x is given by L of y of x. So let me write it g xi f x. Now in place of f x I am writing L of y f. So now truncate this into two part, a to xi g1 xi Ly x dx plus xi to b g2 xi Ly x dx. Now we already know that Green's formula for self adjoint operator is this a to b vlu dx equal to a to b ulv dx plus p naught x vu dash minus v dash u from A to B. So, here using this formula we have A2 xi z1 x xi ly x dx. When you look at this part, this is going to be yx L of g1, and L of g1 is basically constant multiple of y1, and y1 is a solution of L. So, that part will be 0, and what is left is this point here. A is this and B is equal to xi, and when you simplify you will get this formula P naught xi g1 xi comma xi y dash xi minus y xi diver g1 x comma xi diver x at the point x equal to xi. Using this similar formula we can get this part xi to be z2 x xi ly x dx equal to, then again using the same formula here, here you will get y and L of g2, and g2 is a multiple of y2. So, we can write it here, that part is gone to be 0, and using this boundary term here we can simplify our expression as minus P naught xi z2 xi comma xi y dash xi minus y xi diver g2 x comma xi diver x at x equal to xi. So, here we have xi to be g2 x comma xi ly x dx equal to minus P naught xi z2 xi comma xi y dash xi minus y xi diver g2 by diver x at x equal to xi here. So, using these estimates and the continuity property that g1 xi xi equal to g2 xi comma xi and diver g2 upon diver x minus diver g1 by diver x at x equal to xi is equal to 1 upon P naught xi. We can write that A to B gx comma xi f xi d xi equal to y of x. Here also we have utilized the symmetricity property that gx comma xi equal to g xi comma x. Let us just simplify this procedure like this. We have calculated A to xi g1 x comma xi f of x dx equal to P naught xi g1 xi comma xi y dash xi minus diver g1 by diver x at x equal to xi y xi. Similarly, we have calculated xi to be z2 x comma xi f x dx equal to minus P naught xi g2 xi comma xi y dash xi minus diver g2 upon diver x equal to xi y xi. Now, we use this condition. So, let us see A to B gx xi f x dx equal to A to xi g1 x xi f x dx plus xi to B z2 x xi f x dx equal to. Now, use this formula. Let me collect the coefficient of P naught xi. So, P naught xi, let us first use this g1 xi comma xi minus z2 xi xi plus if you multiply here, then P naught xi equal to diver g2 by diver x at x equal to xi minus here diver g1 by diver x at x equal to xi into y of xi here. Now, because of continuity this part is 0, and because of jump discontinuity this part is going to be 1 upon P naught xi. So, 1 upon P naught xi and P naught xi is here. So, that will cancel out and we have only y xi. So, it means that A to B gx xi f of x dx equal to y of xi here. So, now just interchange xi and x, and we have y of x equal to A to B g of xi comma x f of xi d xi. But here we have noted down that g of xi comma x equal to g of x comma xi, because in self adjoint problems your green function is a symmetric green function. So, in place of g xi comma x we can write g x comma xi. So, we can write y of x equal to A to B g x comma xi f of xi d xi. That is what we wanted to prove, that A to B gx xi f xi d xi is equal to y of x when gx xi is the given green function. So, that is what we have proved here, that A to B gx xi f xi d xi is equal to y of x. So, we have shown that this part, that if gx xi is a green function of the homogeneous boundary value problem, then yx is a solution of boundary value problem, non-homogeneous boundary value problem with homogeneous boundary condition if and only if yx is written as A to B gx xi f xi d xi, where gx xi is the green function given here, which we have already obtained for the homogeneous boundary value problem with homogeneous boundary condition. So, once we have this result proven, Then again let us consider one example based on this, and here find the green function of the problem y double dash equal to 0 together with the boundary condition y alpha equal to 0, y beta equal to 0, and hence solve the boundary value problem y double dash equal to f of x comma y dash with y of alpha equal to a and y beta equal to b. So please look at here we have a this non-homogeneous problem and non-homogeneous boundary condition as well. So first thing is, let us find out the green function for the homogeneous problem. So if you y double dash equal to 0 means yx equal to c naught x plus c1. Now if you use y alpha equal to 0 and y beta equal to 0, you can say that we have only trivial solution. So only trivial solution exists means your green function exists, and let us write down the green function as gxt equal to ax plus b, where x is lying between alpha to t and cx plus d when x lying between t to beta. Now we want to show that that gxt satisfy the boundary condition at alpha and beta. So using this, since this gxt satisfy the boundary condition, so it means that this ax plus b will be 0 at x equal to alpha. So that will give you that a alpha plus b equal to 0, and y beta equal to 0 implies that c beta plus d equal to 0. So this reduces to since green function is continuous, we have one more condition that at plus b equal to ct plus d, and using the jump condition we can write double g by double x from x t plus minus t minus equal to 1 upon pt. Now here pt is what? Here pt is basically 1 here. So using this we can write that c minus a is equal to 1. So c minus a equal to 1 and at plus b equal to ct plus d, and some more condition is given. So using this we can get our solution a, b, c and d. So once you have a, b, c, d, then we can write down gxt as 1 upon beta minus alpha, beta minus t, alpha minus x when x is lying between alpha to t, and alpha minus t, beta minus x when x is lying between t to beta. And if you remember, the proposed problem is self-adjoint problem, so you can say that gxt is also looking at symmetry problem. So here we have utilized all the 4 condition that gxt satisfy the boundary condition, as well as gxt is continuous and gxt has a jump discontinuity at x equal to t. So using this we have gxt. So once we have gxt, now we want to solve the non-homogeneous problem, but before solving the non-homogeneous problem we have to convert the non-homogeneous boundary condition to a homogeneous boundary condition, and for that we consider a linear change which we have already discussed, zx equal to yx minus beta minus x upon beta minus alpha into a plus x minus alpha upon beta minus alpha into b. Again I request that you do it, zx equal to y of x plus some gamma 1 x plus gamma 2, and you need to find out what is gamma 1 and gamma 2. So when you fix it you will get this result here. So then our problem is now reduced to z double dash t equal to f tilde t comma z dash t, where z alpha equal to 0 and z beta equal to 0 here. So now we can write down our solution of this non-homogeneous problem is now z of x equal to alpha to beta gxt and f tilde t z dash t dt. Now we already know that yx is yx and zx is connected by this formula. So using this we can write down yx equal to zx plus this. So when you write beta minus x, beta minus alpha a and so on, plus alpha to b gxt f tilde t z dash t, when you rewrite in terms of x then it is coming out to be ft yt y dash t dt. So your solution is now given by this particular formula, that y of x equal to beta minus x upon beta minus alpha into a plus x minus alpha upon beta minus alpha into b plus alpha to beta gxt ft yt y dash t dt. Now here everything depend on this function f. If this function f is independent of yt and y dash t, then we will have a closed solution. It means that we can find out the explicit formula of y of x, but if this function f is not independent of yt or y dash t, then this is basically a integral equation. So it all depend on the form of f here. So let us take a particular form of this f and see one more example here. So using Green's function, solve the boundary value problem y double dash x minus y of x equal to x, y0 equal to y1 equal to 0. So this time we are considering the homogeneous boundary condition and non-homogeneous problem. So first find out the solution Green function for the homogeneous equation with homogeneous boundary condition. So find out y double dash x minus y of x equal to 0, y of 0 equal to y of 1, and we try to find out the solution here, and we can say that general solution of the corresponding homogeneous boundary problem is y of x equal to a e to power x plus b e to power minus x, and when you apply the boundary condition, we can say that a and b are both are coming out to be 0. So it means that we have only a trivial solution of the homogeneous boundary value problem, and hence your Green function exists. And Green function we can calculate in this form. I am leaving it to you, that you find out that gx comma xi is equal to sin hyperbolic x sin hyperbolic xi minus 1 divided by sin hyperbolic 1 when x is lying between 0 to xi, and sin hyperbolic xi sin hyperbolic x minus 1 divided by sin hyperbolic 1 when x is lying between xi to 1. This I am leaving it to homework, and you can see that this is a symmetric Green function, and the solution of the boundary value problem is given by yx equal to 0 to 1 gx xi, and f xi is basically x here, f xi is xi here. So fx is equal to x, so f xi is equal to xi. So 0 to 1 gx xi xi d xi. Now gx xi is known to you and xi is also given, so you can write down this integration into two part, 0 to x and x to 1. So 0 to x xi sin hyperbolic xi, here when you look at xi is less than x, so xi less than x means this part. So in first integration you use xi is the function sin hyperbolic xi sin hyperbolic x minus 1 divided by sin hyperbolic 1 d xi, and in this xi is greater than x, so you use this part. So xi sin hyperbolic x sin hyperbolic xi minus 1 divided by sin hyperbolic 1 d xi, and you solve it, and you can use this following result, that 0 to x xi sin hyperbolic xi d xi equal to x cos hyperbolic x minus sin hyperbolic x, and x to 1 xi sin hyperbolic xi minus 1 d xi equal to 1 minus x cos hyperbolic x minus 1 plus sin hyperbolic x minus 1. So these integration you have to solve. I think it is not very difficult, that is why I am using a simple result here, and we can write down our solution as this, y of x equal to sin hyperbolic x and divided by sin hyperbolic 1 minus x. So here we have solved the non-homogeneous boundary value problem with homogeneous boundary value problem with the help of Green function for homogeneous boundary value problem. So this is one very important use of Green function, and since here your right hand side is independent of y and y dash, so we are getting the exact solution, means we are getting the closed form of the solution, not an integral equation. So with this I conclude our lecture. So in this lecture we have seen that under what condition our Green theorems Green function exists, and with the help of Green function which we have obtained for homogeneous equation with homogeneous boundary value problem, with the help of this we can solve a non-homogeneous equation with non-homogeneous boundary value problem. So that is all for this lecture. We will continue in next lecture. Thank you very much for listening. Thank you.